Yes, class. Is this audible? There's some issue with my network. Okay, Fahad, I'll wait for 2 more minutes. Fine, you just fix your network issue, whatever is the issue. Rest of the class, is this audible?
Yes, sir.
Right. So now in the last class we had started with Ampere's circuital law. Remember? Ampere's circuital law we had done where Ampere's circuital law basically said what? It was a magnetostatical analog of Gauss theorem. So Ampere's circuital law basically said that closed integral of magnetic field that was equal to mu naught times, that is permeability times the current enclosed. This was Ampere's circuital law. Ampere's circuital law was equal to what? This was equal to P dot dl closed integral was equal to mu naught times the current that was flowing. Fine. E is equal to B dot dl is equal to mu naught. Now C class. There are two applications of it. Applications of Ampere's circuital law are two. One is known as solenoid, other one is known as toroid. Please remember the formulas at the end. These are important because these will be used till your AC. Alternating current lesson. Solenoid will be used. At least solenoid's formula will get used. Now, what is meant by solenoid? Let's start with solenoid. Solenoid, toroid, these are easy topics. These are not so tough, but it can be confusing if you do not revise both of it. Solenoid and toroid. Now, what is meant by solenoid? Solenoid is basically when insulated copper wires are wound together in the form of coils. This is known as a solenoid. Solenoid is nothing if a normal wire has been converted into coils with certain n number of turns, that we call it as solenoid. Now, here what happens? Current will be entering from here, then current will come out of the page, then it will go back from here, then it will come out of the page, go into the page, come out of the page, go into the page, like this, because these are coilings. So in case of solenoid, we will not write the derivation directly like this. Using this solenoid, no, we won't derive the formula of magnetic field for the solenoid. One more important thing, remember, see, outside this solenoid, magnetic field is zero because there is no presence of magnetic field, nothing is there, so we write it as zero. Now, coming to the main point that I was telling, yes, we do not write it directly. What we write instead, no, we take a middle section of this. Here what happens? Magnetic field lines are going out, going in, coming out again, going into the page. Are you able to notice this? Like this was the windings of the coil. So what happened? If current came out, so from here the current, let's say, is coming out, then the current is going into the page, So like this we are drawing it. So all these are outwards. All these are inwards. Fine. Now we will take a very small rectangular loop in this manner. That is not completely enclosing your solenoid like this, and it is not also lying completely outside of it, covering a certain portion inside, covering a certain portion outside. So proper rectangular loop we have written. Let's name it as ABCD. L is the length of it. L is the length of the rectangular loop. So this is a sectional view of long solenoid. If you cut it like this and you're able to observe this point and this point, at this point current will either enter or leave, at this point current will come out or leave, corresponding to what happened. So that's how what we have drawn. This derivation is very easy, class. This is very easy. It is as compared to those derivations of drift velocity and all these derivations of magnetic fields that you have studied. These derivations are very easy derivations. Class, at least give a test of these application of magnetic fields in the next class. Not magnetic field. Magnetic field means basically Biot-Savart's law. Biot-Savart's law is completed. Applications of Biot-Savart's law is also completed, and all of you have attempted that, attended those classes. So next week, let me see the date. 22nd is Monday. No, you people have your next class on Thursday. And after Thursday, leave Thursday, don't give the test on Thursday. Uh, 22nd, 23rd is Tuesday. Tuesday then. Today is 16th, so leave Thursday. Thursday we'll have a regular class on 23rd. Please give a test on Biot-Savart's law and application of Biot-Savart's law. Biot-Savart's law general formula, Biot-Savart's law, and its application. Application means all those derivations which you have done in the last class. Till the last class, magnetic field for a circular loop, magnetic field for the axis of a circular wire, all these derivations, right? So just that portion at least do it. You'll be at least clear by the side of Biot-Savart's law. So please remember, only what?
Only derivations or numericals will be there?
Numericals will also be there. Numericals will also be there. Proper these terms. All these which you have studied, no, the derivations as well as the formula, as well as the question, everything regarding Biot-Savart's law. Before Ampere's circuital law, know what you have studied till then. So Fahad, yes, your internet was there. See, we are discussing applications of this Ampere's circuital law. So solenoid is basically a device. Solenoid has various turns of copper or insulated wire, any device like this. So that is known as a solenoid. It's based. So in your exam, no, you can be asked to apply Ampere's circuital law and calculate the magnetic field inside solenoid. Like these questions can come. So solenoid means only channel. Means channel. So that's why we have solenoid is what? Basically insulated copper wire wound closely in the form of a helical, like this, what you have, what I've shown you in this figure. So that is meant by solenoid. Now, what happens at this point? Current is entering, then current is coming out, then current is entering, current is coming out. Or we can say vice versa. If we shift the direction of current, current enters from here, comes out from here. Like that we can say. But for the derivation of magnetic field inside the solenoid, see these are the coil. If you just look at these portions of the coil, at one point you will see current that is going into the page, other point you will see current is coming out of the page. So that we have written in this manner, dots for sure that are showing outwards and these crosses that are showing inwards. Fine. So these are certain things. Now comes the application part. Application part of what? Application part of the Ampere's circuital law. So Ampere's circuital law, you people have remembered it. You people remember it. B dot dl is equal to mu naught times the current enclosed. This we have discussed a lot of times. So now the B dot dl will be written how? It won't be a single B dot dl. Line integral will be not single because the Amperian loop that I have chosen, this is ABCD. So it will be magnetic field line due to this magnetic integral of CD plus magnetic integral of AD. This derivation is very easy, derivation of both of these solenoid toroid, and very scoring. Just listen it once carefully. So it will be what? B dot dl plus integral of B dot dl plus integral of B dot dl plus integral of B dot dl. Means what? From A to B, then B to C, then C to D, then from D to A back. Now we just have to put in all the values of it. Just look at BC and AD. Look at BC and AD over here. If you look at BC, this side is BC, and if you look AD, see what is happening. What's the angle that is formed between DL and magnetic field? Magnetic field is 3D coming out of the plane. Your loop is straight like this. What's the angle that is formed between them? 90 degree. These magnetic field lines are coming out. This is like this. So if your AD is like this and magnetic field is coming out of the page, so this angle is 90 degree. So it means B dot DL cos 90 degree, and here also B dot DL cos 90 degree for both of these. So leave this right now. For BC, it becomes BDL cos 90 degree, as well as for AD, this will be BDL cos 90 degrees. Now what is left? B dot DL of A to B and B dot DL of D to C are left. Now D to C is very easy. D to C is what? If you look, D to C or C to D, this part is lying where? This part is lying out of the solenoid. So out of the solenoid, what did I tell you? Magnetic field out of the solenoid at any point that you have magnetic field out of it, that will directly be what? 0. So it means this B dot DL is also 0 this time, because magnetic field is 0. So if magnetic field is 0, definitely that will also be 0. So magnetic field is 0, 0 dot DL. Fine. And what are we left with? We are just left with BL. Simply BL, if L is the length. What are we left with now? BL, this becomes 0. 0 multiplied by DL is 0, plus BDL is 0. So we have solved this BDL, this is BL. Fine. This is just BL. L is what? L is the length of the side of the rectangle ABCD. I'll write it down as well. L is what? L is the length of the side AB of rectangular loop ABCD. So L is length. Now small n is what? Let's say small n, this is the number of turns per unit length. Not just number of turns. Please class pay attention to this. Number of turns and number of turns per unit length. Because this becomes so confusing at the end if number of some students use small n, some students use capital N. There's a difference between both of them. Small n is number of turns per unit length. It means if number of turns is n and L is what? L is the length. So small n can be written as capital N divided by L. Remember this. Fine, class. Now number of turns in length L, what will it be? If number of turns per unit length is small n, unit length, number of turns are n. So for L length, L is the length of the rectangular loop, it will be n into L. Simply unitary method. So now the current of the solenoid will become n times. It will become n times the current that is flowing. So number of turns of the solenoid is NL, that we have studied now. Discussed this way also. We have discussed it in this way as well. So B dot DL will be equal to what? Now let's match it. B dot DL is equal to mu naught times the current enclosed. B dot DL, we have received it as BL, mu naught. Now current won't be I. Current will be, this is current for a single turn. For this much turn and for this much length, current will be NL into I. L gets cancelled, B becomes equal to mu naught Ni. Remember this. This is a very important formula, and this derivation is also very easy. If you wish to write it in terms of number of turns, this becomes mu naught capital N divided by L. Why? Because this is number of turns per unit length. See, capital N is number of turns. And this is what? This is number of turns per unit length. So both of these formula are equal. It's just that whatever is given to you in the question, use both. Use any of these, whichever. If number of turns are just mentioned, yes.
This is the formula of solenoid, right?
Yes, yes. Magnetic field inside a solenoid. Inside. Outside is always zero. Magnetic field inside is solenoid. This formula, please remember it. Derivation is very easy. See, just make this diagram. AD, BC are automatically 90 degree making zero. CD is out of the plane, so we write it as zero. BL is left, so one side is BL. B is equal to mu naught I is there. For NL length, it will be NLI, so you get the final formula in this manner. It's very easy. Derivation is very easy, but it is very important. So note down this, then we'll see what's the there's a very slight difference between solenoid and toroid. Once understood solenoid, then it will be very easy for you to understand toroid. Just a slight difference in a derivation and the formula.
Can you scroll down?
Yes, yes. Okay. Fine. Okay, Matthew.
Ma'am, here any one formula we can use.
See, whatever is given to you. If in the question, for example, the question says that a solenoid is there with the number of turns as 200 turns per centimeter. So I'll use the first one. If it is given a length of a solenoid is 50 meters and the number of turns is given as 200 turns, then you'll use the second. So whatever is given to you, according to that you'll use. If number of turns are just mentioned, then do not use the first formula. That's why I've specified it. Fine. So whatever is, we'll do questions. We'll do question right now, and let us just complete toroid.
Okay.
And we'll complete questions. So written class.
Yes, done.
See, toroid is now, understanding of toroid is easy, and the derivation is also interesting and easy. If you just turn the solenoid in the form of a closed ring, then we call it as a toroid. Means solenoid was what? Solenoid was a straight long wire like this. If you curl it, if you turn it into a form of a closed ring, this is what is known as a toroid. That's the basic difference. A solenoid bent into the form of a closed ring is called a toroidal solenoid, also it is called, or it is known as toroid. Basically, torus word means ring. This means ring. So this is in the form of ring. Similarly, here what will happen? Current will go, then current will come out from here, then it will go from here, it will come out from here, and so on. The way whatever happened in case of a toroid, that will be the same. Now what will happen? Again, if you have this, you just focus on these portions. These two, what will appear at this end? It will appear that current is coming out. At this will appear and that current is moving in. Similarly, at this point it will appear that current is moving in. At this point current is moving out. So the best way to derive it, derivation is very easy. Just understand the figure once. Derivation is easy. So we are just writing in terms of closed ring. So here, if let's say the current is coming outwards, this is that end where the current is coming outwards. It's in the form of a coil only, simple coil only. It's just that current is coming out. Here current is going in. So it's in a continuation like this. Current is coming out, current is going in, then coming out, going in, coming out, going in, like this. Fine. Now we have to choose our Amperian loop. But for choosing the Amperian loop, we'll divide it into three regions. Let's say this is first region, this is the second region, and this is the third region. So we'll calculate it one by one for the first region, for the second region, for the third region. So for the points in the open space interior to this toroid, this open space interior to this toroid, interior one, region one, let me write down it as region one. See, derivation is very easy, just pay attention. Region 1. I have to choose an Amperian loop. See, if I choose an Amperian loop for this region, this is the best possible Amperian loop that I can take. Let's say radius R1 is the radius of this region. So class, what is the magnetic field? Is there even a single magnetic field that is getting enclosed within this region, region 1? Yes or no? What do you think about the magnetic field, class? Look into the figure. Yes, answer. Is there any magnetic field that you people think is included within this? Yes, Fahad.
0.
Zero. Definitely it will be zero. Reason being there is no magnetic field in this region. It's the interior. What happened to the solenoid? Solenoid is now in the form of a circle. So in region 1, when you apply B dot dl is equal to mu naught I, B1 in the first region is 0. So magnetic field in the first region came out to be 0. Let's talk about region 2nd. Now we'll choose an Amperian loop within this. This is the Amperian loop that we'll choose. See, this is the Amperian loop. R2 is the range. This is the Amperian loop for the second region. Fine. Now I have to write what? I have to write B dot dl is equal to mu naught I. Now I cannot just write B dot dl. B dot dl is equal to mu naught I. That's fine. But what is integral of dl? See, magnetic field is B. Integral of dl for this circle, this will be simply 2 pi r, 2 pi r2 actually. So this will be simply 2 pi r2. This is equal to what? This is equal to mu naught, and if n is the number of turns, n into I. If n is the number of turns, then total current enclosed will be C. Total current enclosed will be equal to n multiplied by I, where n is number of turns. Now see, what is left with us? What is the magnetic field that I am obtaining? From here I am getting B is equal to mu naught n capital I divided by 2 pi. R2 let's not write, because let's write it as R only. Let's write it as R only, because you will see why there is no need to mention it separately. C class, in the third region, only region 3 is left. Region 3 is outside. Even if you choose an Amperian loop for this region, C class, this is lying outside. This region 3 is lying outside. So magnetic field in this region will also be 0. So for the third one, region 3, magnetic field 3 is 0. So what's the total magnetic field? Total magnetic field is mu naught Ni divided by 2 pi. That's why I was saying, do not mention it as R1, R2, R3 or any, because single radius is involved, so you can write this. Now this is the formula. B is equal to mu naught I divided by 2 pi r. Now what is N divided by 2 pi r? N is what? N is the number of turns. 2 pi r is what? 2 pi r is circumference or length of circle. So this becomes what? Number of turns per unit length. So we can again write B as mu naught Ni. B is equal to mu naught Ni. Where your small n is what? Small n is equal to capital N divided by 2 pi r. Number of turns per unit length. This is number of turns per unit length. Fine, so both the formulas are B is equal to mu naught Ni. And I hope you people know mu naught is 4 pi into 10 to the power minus 7 Tesla meter per annum. This value is also used. This will be used in your test also. B is equal to mu naught Ni. Just the difference is that N here is number of turns per unit length and length is length of a circle. Here number of turns per unit length is straight away a single length. Fine. So quickly copy this toroid, then we'll start with the questions for it. At least let's do certain questions. So before Ampere Circuital law, I'll take the test on the next Tuesday. Not the Thursday's class. Thursday's class we'll have the normal theory class. On Tuesday, I'll take the test. That is 23rd of August. Test syllabus is just magnetic field for all those things that we have done. Basically, Biot-Savart's law and application of Biot-Savart's law. So before everything, before Ampere Circuital law, that we have to include in the test. See region 2, Fahad. Region 2 is this. So in this region, if I write B dot dl is equal to mu naught I, dl is what? Integration of dl is what? We have studied so many times that if you integrate all the values of these infinitesimal lengths, that is dl, that will give you complete length of a circle, that is L. And L for a circle is what? 2 pi r. So this side, left hand side solved, B into 2 pi r. Right hand side, mu naught I we cannot write it for a single turn. What if n number of turns are there? Obviously n number of turns are there. That's why we are considering it as a solenoid, it as a toroid. In case of toroid and solenoid, you don't have a single turn, you have number of turns. So for all the turns, we'll write the current enclosed as Ni. So from here, just shift the value into the denominator. So B comes out to be mu naught Ni divided by 2 pi r. Clear, Fahad? And inside and outside, these are 0. So ultimately, magnetic field is this. So did you people make this figure, students? I'm scrolling it. If anyone wants to scroll me back up, let me know. All right, Zed. Now I'm giving you questions. So all those who have noted, at least try with the questions. C class. This is written what a solenoid of length 0.5 meter has a radius of 1 centimeter and it is made up of 500 turns. It carries a current 5 ampere. What is the magnitude of the magnetic field inside the solenoid? That you have to tell. And it's an important question because it's a question from your NCERT. Now, number of turns per unit length is what? Number of turns are given to you as 500 per unit length. Length is given as 0.5. So this becomes 1000 turns per meter. So B is equal to mu naught Ni. Mu naught will be 4 pi into 10 to the power minus 7. N small n is 10 to the power 3. Current is 5. So this comes out to be 6.28 into 10 to the power minus 3 Tesla. 6.28 into 10 to the power minus 3. Yes, Zaid, right. Sahal, I think, slight error in the calculation. Did you get it, Sahal? And only Tesla.
Right.
Only Tesla, because magnetic field
Okay.
is the unit is Tesla. All right.
Okay, ma'am. Got it.
Try this question at least. Yes, class answers. Yes, that's right. Has actually come in CBSE papers, these foreign papers of 2004, and once an ICSE board also. 1.9 into 10 to the power minus 3. Yes, right. It has this exactly is the second question. First question is from your NCRT. The second question has come in CBSE foreign 2004 and in the ICSE board. Now C class, here number of turns per unit length, 300 turns per meter is given. So no need to convert it or write it. Small n is given to you this time, not capital N. Capital N divided by L is given to you, 300 turns per meter. Length is 0.5, radius is 1 centimeter. Why is this data given in both the questions when it is not utilized? Reason is that this just shows that length is greater than the radius. It means it is a long solenoid. Just for this fact only, the radius and length are given. Current is given 5 ampere. Okay, same current is given. So B is equal to mu naught Ni. B is equal to mu naught N into I. B is equal to, this is 4 pi into 10 to the power minus 7. Small n is 300. I is 5. So this will be 0. Or let's write it in terms of powers of 10. 1. When you'll solve this, this will be 1.9 into 10 to the power minus 3 Tesla. All right, note it down. Done class, written. Once you have written this, just text me done in the chat box so that I get to know who all have written, who all have not. All right, so I think most of you have completed. If anybody is writing, then just stop me, then I'm moving to the next topic. We can at least start with the next topic. Obviously, magnetic Lorentz force will not be completed, only 15 to 20 minutes a day. See, magnetic Lorentz force is what? Magnetic Lorentz force is very easy. Magnetic Lorentz force basically gives you the path of the charge in magnetic field. Before moving into the actual magnetic Lorentz force and everything, just understand, see a charge is there, q charge is there. This is moving with v velocity at any random direction, making an angle theta with the magnetic field lines. Fine, that's what I've written. Charge q is moving with velocity v in a uniform magnetic field. Uniform magnetic field is what? B. So we are just seeing the motion or the path of the charge in this magnetic field. So magnetic force is what? Magnetic field exerts a magnetic force, and this magnetic force is charge and the cross product of velocity and the magnetic field. Charge into V cross B. So FB is written as QVB, where see what is meant by each term. See, FB is what? FB is the magnetic force. Q is the charge. So if it's an electron is moving, then that will be electronic charge, which is 1.6 into 10 to the power minus 19. If it's a proton, then that also will be electronic charge. If it's a random charge, different charge, that charge value will be given to you in terms of coulomb. V is what? V is the velocity of the charge particle. And B is the magnetic field. So this is an important formula. No derivation in this formula. Just remember, FV is equal to Q V cross B. This is magnetic field. So since no derivation is there, directly remembering this formula becomes important. Now, before you note this down, just remember this formula. See, one certain points that come from your theory point of view, very short questions from your 1 markers or 2 markers. See, if it's a condition that force is perpendicular to velocity. So if force is perpendicular to velocity, then obviously everybody knows in this class that velocity is what? Rate of change of displacement. So if force is perpendicular to velocity, force will also be perpendicular to displacement. And what is work done? Work done is F dot S, which is Fs cos theta. Now here the angle is what? 90 degree between the force and displacement. This is which case? If force is perpendicular to velocity. In this formula, F is equal to QB cross B. So this becomes Fs cos 90 degree, which comes out to be 0. Fine. So what can be the question? If the force and velocity both are perpendicular to each other, then what is the work done by the charge in the motion or in overcoming the magnetic field, whatever is just. First theoretical point is what? Work done will be 0. No need to perform any calculation, no need to perform any of the derivations. Directly remember it as 0. Now, connecting it to your work energy theorem. See from here. Work energy theorem says what? Work energy theorem says all the work done that has occurred. All this work done is what? All this work done is basically converted into the change in the kinetic energy. That is kinetic energy final minus kinetic energy initial. So if work done is 0, then this change in kinetic energy is also 0. Why are we writing all these things? These were included in class 11. Why are we writing it in class 12? Because your theory questions, if the paper comes tough, then these questions can be asked. If force is perpendicular to velocity and a charge is moving in uniform magnetic field, what is the effect on kinetic energy? So how will you relate? You will relate by these steps. And these are just for your theoretical questions. No formula, no question is going to come, no numerical is going to come from these. So kinetic energy final is equal to kinetic energy initial. It means no change in kinetic energy. This means no change in the velocities as well. All right, these are certain important points that you should remember. So if force is perpendicular to velocity, work done becomes zero. There's no change in kinetic energy. So initial kinetic energy is equal to final kinetic energy, which states that initial velocity is equal to final velocity. This is the maximum difficult theoretical question that can come, maximum, from this topic, magnetic force. And what is magnetic force? Charge and the cross product of velocity and magnetic field. So note it down here. Any doubts, ask me. You're free to ask any doubts from this topic.
Ma'am, this one is a formula of Lorentz force.
Yes, this is the formula of Lorent force. Magnetic force, whenever magnetic force is specifically asked, this is given. Now we'll see a specific case also. If the charge is placed in not only just the magnetic field as well as the electric field, then we'll see the modification of the Lorent force. But in the exam, if it is given that a charge is placed in a magnetic field, then just write this formula, because no derivation is there. But in the exam, this formula is not asked directly. Only questions are given and the applications are done. Clear?
Yes, ma'am. Why the work done is 0 here?
See, work done is 0 because force and the dot product of force and displacement gives you what? The dot product of force and displacement gives you work done. So here in this case, force is perpendicular to velocity, that we have assumed, and in the questions also this will be provided to you. So if force is perpendicular to velocity, force will always be perpendicular to displacement, definitely, because you know for velocity is what? Rate of change of displacement. So if force is perpendicular to displacement, then angle between them is 90 degree. So cos 90 is what? It's 0. So that's why we have work done as 0. And when you apply the work energy theorem, all the work done gets converted into change in kinetic energy. So here you have the change in kinetic energy also as 0. Both of these terms become 0. Got it?
Yes.
And this force is perpendicular velocity will be given to you in the question. Just text me done, all of you, if you have written it.